All right, so today we have Shani Meynet, who will tell us about boundary geometry and topological defects. Take it away.
Thank you very much, Julius, and thank you for the invitation and the chance to talk here today. So this work I'm going to present, the talk I'm going to present now is based on two works, one made in collaboration with Michele Del Zotta and Robert Moskrop, and another more recent one with Mario De Marco. And this, okay. So a few words of introduction, and I have to click the button, otherwise it doesn't work. So in the last 10 years or so, a new way to think symmetry, a new paradigm to interpret symmetry in quantum field theory has been proposed, starting with this seminal paper in 2014, where this double arrow was established. In previous literature, we knew that to symmetry we could attach topological operator, basically by the construction via conserved current alla Noether. One has a conserved current, to a conserved current one can associate a charge, and the exponentiation of a charge leads to a symmetry operator. Because of the conservation equation for currents, the operator once defined from the because of the conservation equation for currents, the operator one defines using the charge is topological and doesn't depend on its support. So we have the arrow from left to right, symmetries to topological operator. However, allowing ourselves to draw the arrow in the opposite direction, so associating topological operator to symmetries, enriched, widened the possibilities of what we would call a symmetry, and so what we would call a conserved quantity, what we would call a relation in a quantum field theory, and this allowed to use different type of object, not only group-like object, but say categorical object to constrain quantum field theory, new kinds of word identities, new kinds of relation among amplitudes, a set of tools that allows us to constrain further quantum field theory. So it became really interesting to understand better what are the topological operators for quantum field theory, because they can be used to learn much more about the theories of interest. And a lot of work has been done in the last decades, and this work is too much to be all referenced here, so I will keep references to a minimum, but a lot has been done by many, many people, and many of them are also in the audience today. So what has been learned so far about this topological symmetry? Well, one important aspect is that there's a handy tool to encode all these topological operator in a unifying framework. And this tool is called the Symmetry Topological Field Theory, or SymTFT, or SymTFT for short. This is a d+1 dimensional topological theory that one can associate to each dynamical d-dimensional theory that encodes all the information about topological operator. So far, the literature is pretty solid in the context of finite symmetries, and I will talk today mostly about finite symmetries. However, I have to remark that some work has been done also for continuous symmetries, but we will not delve with them today. The SymTFT is really useful to capture this aspect because in a sense it's a sort of a dynamical theory for background fields. So let me show through a picture how this thing works. In particular, this is also called the sandwich picture. We have the following. When I talk about a quantum field theory, I usually talk of a relative theory, or like in a sense, it's talking about the group, the algebra of the gauge theory instead of the group. So if I take, for example, SUN, Yang-Mills, when I write the Lagrangian, I write down something that depends only on the algebra of the group, whereas the global structure, so whether I'm dealing with SUN or PSUN, that's depend on some topological boundary condition that I have to impose. This slice of the sandwich will represent, in a sense, my Lagrangian, my relative theory, the group the algebra that I'm picking, whereas the boundary condition, the topological boundary condition on the other side of the sandwich will represent which global variant of my quantum field theory I'm considering. And the SymTFT just fills between these two boundaries, where all the topological operators now are represented as extended operator that lives in this topological theory. They link with each other, they have some sort of interaction. I will not enter much of the details there. I will just mention when this becomes relevant. But this is the way we think of at least topological finite symmetries these days. So you have an absolute theory on one side, and you have a way to pick which symmetries are realized in this theory, which are the global variants of your quantum field theory. And this picture, which is a quantum field theory construction, can be extended to be a geometrical construction. Indeed, one of the most interesting results of string theory is the possibility of constructing quantum field theory starting from geometrical data. And this procedure is described through the geometric engineering dictionary. This is a way to associate to geometrical quantity quantum field theoretical ones. And so it is now interesting to ask ourselves, given these new developments in the study of symmetries in quantum field theory, can we get the same information from geometry? And if so, how do we do that? In particular, the geometric engineering dictionary associate, for example, to exceptional divisor in geometry, so cycles you blow up to make a singular geometry smooth, particles. And so if you want, I will show, for example, some example of how to engineer Young means in various dimensions using different geometries and how the quantities of the quantum field theory are associated to geometry. But so this dictionary tells us how to build a particle, how to build heavy defects, which we can think of as Wilson lines or Toft surfaces in various dimensions, and tells us as well that there's a way to get topological operator from the boundary geometry of the engineering one. Everything will become a bit more precise when I go into the details, but so far let us acknowledge that some work has been already done and something has been already understood. However, this is not the end of the story, and I will show that this this three-level way of studying topological defects from boundary geometries needs to be supplemented with extra ingredient to fully capture the whole structure of the topological operator, the whole interaction, and all they teach us about our field theory. So starting from new result in quantum field theory, we ask ourselves, what are the consequences? How can those results be read from geometry? And in this talk, I will explore exactly these facts. First of all, I will start with 7D super Young Mills, engineered in M theory on some twofold singularities. This theory will represent a sort of toy model in which everything can be done very explicitly and everything can be shown step by step, and makes everything, all the ingredients that I will use clear. In particular, we will recover the defect group, so basically the center symmetry of Young Mills, 7D Young Mills, directly from geometry. And we relate this fact to the so-called linking numbers, a topological invariant quantity that can be explicitly computed, defined in the boundary geometry, and so that I will show how this enriches the dictionary of geometric engineering. I will also discuss automorphism of the engineering space and how they can have non-trivial effects on the quantum field theory, can be related to non-trivial symmetries of the quantum field theory. And finally, I will then discuss more rich example, both in 5D and 4-dimensional quantum field theory, engineered as well in M theory using different kinds of geometries. As a summary of the main result of this talk, just to give the final punchline of what I'm going to discuss, I will discuss at length the relation between link and the necessity of enhancing the boundary geometry data with the higher linking data, which captures not only the usual action of symmetry operator on defects, as well captures the anomalies of these symmetry operators. On top of that, I will discuss how isometry, an ingredient that so far has been neglected in this context, can play an interesting role in further understanding how the geometry encodes the symmetry of a quantum field theory. And finally, on this note, I will make some more, I would say, some less refined comment on some future perspective of better understanding this relation between isometries and SymTFT. This is something that has been more, I mean, we have an example of this. We don't have like a formal mathematical statement for this fact. I will just present what are the things that we've worked out so far in this context. But the whole point of this discussion will be to tell you what are the things on top of the boundary geometry, the other ingredients you need to consider in order to fully get all the relation among the symmetries in your theory from geometry, as well as what is left to understand. Well, that said, I think we can start with our toy model example, the 7D super-Young Mills theory. This theory is engineered in M-theory by considering M-theory on an ADE singularity. An ADE singularity is nothing but a quotient of C2 by a finite subgroup of SU2. This geometry is a four-dimensional, non-compact local Calabi-Yau geometry. Is a hyperkähler quotient. There's many ways to describe this. We are interested in this singularity because it's been shown that one can indeed recognize the spectrum of super-Young Mills starting from M-theory on these varieties. In particular, we have that when I put my M-theory on said singularity, I can resolve the singularity. The resolution of the singularity will inflate some exceptional cycles. And one interprets this cycle as parameterizing the moduli space of the singularity. So giving a vev to a scalar in my 7D super-Young Mills would correspond to inflating some cycles in the geometry. This makes the singularity smooth. And on this cycle, I can wrap now the tree form of the M-theory. And this will lead to massless photon that I can interpret indeed as a sort of as the photon that comes from the Higgsing. Indeed, I'm giving a vev to some scalar, I'm Higgsing my super-Young Mills, I'm Higgsing through some adjoint Higgsing, and so I will have photons that goes around. These are interpreted as the dimensional reduction of the tree form of M-theory on these exceptional two cycles. And then dynamical BPS particles will be obtained by wrapping M2 branes now on the same exceptional cycles. And we interpret these massive particles as the W bosons. The mass of this particle would depend on the volume of the inflated cycles. And on top of that, I was mentioning before, one can engineer, these are like the massive particle in the generic point of the moduli space. One can also obtain the extended operators like Wilson line. What is a Wilson line is nothing but the word volume of an infinitely massive particle. So in this context, what is an infinite massive particle? Well, it's an M2 brane wrapped on an infinite cycle that in geometry becomes a relative cycle. Relative cycles are here on the left, and through some manipulation and Lefschetz dualities, one can re-express them in terms of homomorphism of the lattice of mass of the BPS charge. This allows us to make the correspondence between the root lattice of the gauge group corresponding to the W bosons that is encoded by the cohomology of the resolved geometry, and the weight lattice that captures instead the Wilson lines of the theory. This is a well-known fact also if you think about the usual for the SUN Young Mills theory. If you have a pure Young Mills, you have that Wilson line are labeled by the weight lattice, so they have representation like the fundamental, symmetric, antisymmetric, so on and so forth, whereas the W bosons, so the A mu fields, they are in the root lattice, and so they have they are in the fundamental and product of the fundamental. They have zero anality. So okay, this is just to make the correspondence between these two theory a bit, the geometry and the field theory a bit clearer. From this correspondence, now we can read what is called the defect group. The defect group is just a way to, is a name we give to the set of extended symmetries of our theory. These are the symmetry that acts, for example, on Wilson line or top surface and other extended operator in our theory. In Yang-Mills theory, we have that the Wilson line cannot be broken unless some matter is present in the theory. If you have matter in the fundamental, it will be able to break Wilson lines in the fundamental. If you have matter in the symmetric, it will be able to break Wilson lines that have, say, anality 2, and so on and so forth. This screening, first put on by Toft, I think, the idea of screening of Wilson line via charged particles can be translated into geometry through this quotient. I have that the extended objects that are associated to relative homology modeled out by the compact object, like a compact cycle. This screening is exactly Toft screening, but through geometry. This then tells us that defect groups, so the groups that is left over, so the symmetries that acts on the charged lines that are not broken by the particles, is what we call the DN. And let me notice that using some long exact sequence that I will show in the next slide, actually not this one, but this thing can be explicitly computed through some homological means. So if I know nothing, if I have even a non-Lagrangian theory, a super weirdly complicated object, I can still extract this data directly from geometry. And in particular, it turns out that these quantities don't depend on the resolution that I perform. So it's a purely topological global data of my theory and doesn't really depend in, say, which chamber of my modular space I'm finding. It is a global phenomenon that is for the theory itself, not for the local description in a sense of the theory I'm using. So with this out of the way, it turns out that in the case at hand, the only the only contribution to defect group comes from the one cycle of the boundary homology. And this, in the case of ADA singularity, turns out to be the abelianization of the group I'm taking as the quotient of C2 in order to realize the singularity. In this picture now, through this long exact sequence, the short exact sequence now, because it terminates here, I see that I can express cycles inside the boundary homology in terms of cycle of the compact homology. So as I said, I'm taking my twofold, I'm resolving it, and I'm inflating some cycles. And there's a way to relate these cycles that I'm inflating to the boundary cycles. And this is done through this sequence. Why this is handy? Well, this is handy because now I'm able to express as a sum of cycles, so in this case, a sum of divisors. I can express with this formal sum what is the generator of the boundary cycle in geometry. And this is a sort of, this will play a role in understanding what is the action of the isometries on this extended operator, as we will show later. So these divisors are obtained basically by requiring that their intersection with any other two cycle as a charge which is a multiple of n, if say Zn is my center symmetry, i.e. I'm requiring that this divisor, the charge of any particle with respect to this divisor is a multiple of n. So no particle will be able to screen these lines. And indeed to be not the trivial divisor. With these requirements and just playing around with intersection matrix of the resolved singularity, you get the expression, for example, for what is the, let's say, the higher from symmetry divisor associated of this, the AN singularity. Okay, now that we have this object, the question and a way to describe this boundary cycle, etc., we are asking ourselves, okay, but how, now that we have this information about the boundary geometry, how do we know how this boundary cycle encodes the action of symmetry operator on lines? This question was discussed in this paper by Ekman, Ubern, Torres, and Zheng, where they proposed that the action of the symmetry on lines that goes through linking this is the same thing of quantum field theory. When you think having a particle in your space-time, you surround it through a codimension 1 sphere, and this is the action of a regular symmetry on your point-like particle. Instead of having a particle, you have a line, then you don't use a sphere, but you use higher codimensional objects. A line is linked by another line, and the measuring is obtained by unlinking the two. This, for example, in the U1 case, it will produce the phase that you get in front of your particle. You say, I have a, this can be done explicitly, say, in quantum field theory. The translation in geometry data is that now the linking needs to happen not only in the space-time where my Wilson line lives, but in the geometry, in the boundary geometry as well. So is a linking in the whole 11-dimensional string theory construction, not only in the space-time engineered, and not only in the space-time transfers to my singularity. So very good. This linking number, this is a picture of what I just said. So we have that my QFT lives in the transfer space here, at the tip of the cone. This will be my, in this case, with my 7D Young-Mills. I have that the blue line will represent, for example, an M2 branes wrapped on a relative cycle that will engineer a Wilson line in the 7D Young-Mills, whereas the red line will be an M5 wrapped on the torsional cycle and on a 5 cycle in Young-Mills. I'm requiring that the linking appearing in the boundary between the blue and the red cycle is mimicked as a linking also in the spacetime, and this is how the action of the branes, the topological operator, is described on the Wilson line. Now here the topological operator would be the M5 wrapped on the torsional cycle. Is there like a formal way to describe what a linking is? And the answer is yes. A linking can be described in terms of torsional cycle. If I have some torsional cycle in a certain manifold, either torsional or non-torsional cycle, actually, I can describe their linking through this quantity. This is a topological invariant quantity that depends not on the cycles, not on their Poincare dual, but on the Poincare dual of the cipher surface. So this is a bit technical, and I have some slides later as a backup if someone is interested in learning a bit more on how this whole construction arises. What I wanted to say here is just that there's a well-defined notion of what a linking is and how it can be obtained. A linking can be between two cycles. So, for example, two circles can link, like the links of a chain. This can be generalized to multiple cycles participating together into a link, as well as to slightly more weird kind of link. We often, they often fell under the umbrella of what is called a Brownian link, which maybe means nothing, but a picture maybe can help understand what's going on. This is a Borromean link, an example of Brownian link. In this case, we have that no two circles is linked together, but the whole structure cannot be pulled apart. And so this weird expression for higher linkings describe this kind of configuration. Those are topological configuration. You can associate a topological invariant. Indeed, there's a Milnor invariant which captures exactly how many times three circle Borromean link together. And the fact that this can be expressed through differential co-cycles is very interesting, because this poses some constraint on the maximal dimension of and the maximal number of branes can participate to a link. So with this in mind, we can ask ourselves, if a brain acts on another brain via linking, what is the most general link that I can construct, given the previous equation that put some constraint on said dimension? Putting all these together, we get the following formula, where we have N2 and N5 is the number of N2 and M2s and M5s participating to the link. K and kappa represents the possible kind of link. What by kind of link, I just mean that they can be either op link as the link of a chain, or this more exotic style of Brownian link. And if you choose this kind of link to be certain quantities that I handpicked for some reason that can be discussed later, but they reproduce the correct result if done so. One gets indeed that for k equal to 1, exactly 1 and 2 branes, 1 and 2 branes, and 1 and 5 can link together, because for k equal to 1, you have 11, 4 and 7 is 11, so 1 and 1. This is just another way. If you wish, this is a more like bottom-up approach. The same result was already obtained by a top-down when they were using differential cohomology in M-theory, reducing the action of M-theory through differential cohomology mean, and they were getting the same result, the same dimensionality, the same constraint on the linking among the possible topological operator. However, this is a more bottom-up. I just ask myself, if I have these branes and I require them to link, what is the most general thing I can get? And the result matches with the known literature. This also is very constraining because k cannot be higher than the sum of n2 and n5. And so it turns out that for k equal to 1, there's only one solution. And for k equal to 0 as well. I will discuss that later. And basically, that's it. There's not much more else that can go on in M-theory. So this ends sort of why we should be interested in linking numbers. If you just look at the boundary geometry, you might get what are the topological operators. You might get the generator of the one for symmetry electric or magnetic, depending if you wrap M2s or M5s, etc. But just the boundary geometry doesn't tell you that there's this action. You need to supplement it with this information about linking number. On top of the linking number, there's another ingredient that has been ignored, and this is given by isometries. And how we can see that? Well, we start by considering biolomorphism, which is a fancy way to say transformation that leaves this polynomial invariant. If one considers biolomorphism of the sum of these IDE singularity, what happens is that upon resolving these singularities, the action of this biolomorphism is of moving around the exceptional divisors in a way that reproduces exactly the auto-homomorphism of the Lie algebra that is associated to the resolution of the group. So as I was saying, if I resolve this group, the homology describes the root lattice of a certain Lie algebra, that is SUN for AN, SON for DN, SON even for DN, and E6 for E6. And the auto-homomorphism of the algebra is you take the linking diagram and you move it around, in a sense. If you do it geometrically, this is encoded in some operation that you do on the coordinates that describe the singularity. Let us see an example explicitly. In the A2 singularity, which is luckily a toric singularity that can thus be described through some toric combinatorics, one can see that the singularity is the singular local, the singularity is given by this fan where Z1 and Z2 are non-compact coordinate. And then upon resolving, I'm introducing the exceptional divisors E1 and E2. There's a blowdown map, which is nothing but a map that relates the coordinate XYZ to these toric ones. If I have this map and I have my biolomorphism, I see that exchanging Y and Z has the effect of changing E1 and E2. So if, as we said, we think of E1 and E2, the exceptional cycles, the ones on the objects that regulate, for example, the masses of some BPS particle, and if we interpret this BPS particle as the W bosons of the SUN 7D superlinear mills, then we see that this biolomorphism has an action on the W bosons. And this action can be through some manipulation, mixing a bit of this outer automorphism with Weil group, etc. One ends up by identifying this operation with charge conjugation on the action of charge conjugation on the W bosons. However, this is a bit more complicated than this, because not all biolomorphisms are isometries, and this can be seen as follows. This can be seen both geometrically and quantum theoretically. Geometrically is because if I blow up my singularity and I have two cycles, if the volume of the two cycles is different, the biolomorphism will exchange them. And since the volume of the two cycles is different, I can tell the difference between before and after applying my automorphism. From a field theoretical point of view, instead, we have that the resolution of my singularity will pick a point in the moduli space. So resolving a singularity is like going a certain point in the moduli space. And if I'm in a certain point in the moduli space, what can happen is that a symmetry can be spontaneously broken. And this happens indeed because the masses of the two W bosons that are exchanged under this transformation is different in a generic point of the moduli space. And so a B-holomorphism is indeed an isometry only on special resolution. And this can be, we have some math that backs it up. There's a nice PhD thesis in which existence and uniqueness condition will be shown for metrics on AD singularities. And so if I have a resolution, I can associate to that resolution a metric. And if this resolution is invariant under, say, the exchange of the two moduli, then the metric will remain the same. And so I have indeed an isometry. Instead, if the transformation change my vacuum or change my resolution, then theoretically this means that I'm indeed in a spontaneously broken phase, whereas geometrically means that I'm going from one metric to another. So this is indeed not an isometry in general. Very good. And now let's see how this symmetry can participate to a higher group structure. As I said before, it is helpful to have at hand the one-form symmetry divisor, this compact divisor associated to the torsional cycle, because now we can see that the isometry, the B-holomorphism I described, as a non-trivial action in this divisor, is exchanging E1 and E2 as the effect of changing this divisor from D to minus D, counting it modulo 3, because the torsional cycle is a Z3 cycle, so it only counts mod 3. This is suggesting that our charge conjugation, let's say, the outer automorphism symmetry or transformation can indeed act, and as it should, because it is known in even Yang-Mills theory that charge conjugation changes the anality of Wilson line. I start with a Wilson line fundamental, I get Wilson line the anti-fundamental, and this is reproduced here through the action of the isometry on the compact divisor, which is then associated to the torsional cycle. This effect is this is again a hint of something interesting going on also at the level of the SymTFT. If I hadn't considered this isometry, I would write down a SymTFT capturing, for example, only the torsional cycle, but I would have missed this specific action, this extra ingredient. I will discuss later in an example where I have an explicit way to write. I have some theories in which the SymTFT can be explicitly written, and I can show exactly what term you would miss if you don't include this isometry in your analysis of the boundary geometry. But this is a case for later. So this concludes the case. This concluded the example in the 7D case. So we have boundary geometry gives us torsional cycles that are the defect group, so are a list, if you wish, of symmetry operator that acts on extended object. On top of that, we have the linking, which is a topological invariant number that tells us how symmetry operator acts on extended operator, and okay, this is another factor. And the third one is that isometries should not be neglected because they can play an interesting role in understanding the, further symmetries, in this case, finite symmetries that arise in quantum field theory that are not directly associated to branes wrapping cycles. Let me stress that so far many work has been focusing on reproducing symmetries by wrapping branes on torsional cycle, and this can be done, for example, for the one-form symmetry of Yang-Mills. But these isometries symmetry have no, to our knowledge, direct interpretation in terms of branes wrapping cycles. It's pure fact about the geometry that is invariant under certain manipulation. Okay, going on with a more involved case in 5D SCFTs. So we started on theory on a twofold, and now let's go M theory on a threefold. If you play this game now with M theory on a threefold, you will get a 5D SCFT. What you have is that, again, you can associate M2 branes on 2 cycles to particles, M5 branes or 4 cycles, again, compact cycles, to to strings, BPS strings. One can have a Wilson line and tough surfaces associated, again, to non-compact cycles. And as before, one can use the long extra sequence in homology to compute the defect group, and so have a list of all the defect of symmetry defects of our theory. In particular, we have that among the topological defect, M2 branes wrapping torsional wall cycle link with M5 branes wrapping 4 cycles, so they are able to measure the charge of BPS string, magnetic strings, let's say, of the 5D theory, whereas M5 branes wrapped on 3 cycle are able to measure the charge of Wilson line engineered with M2 branes, non-compact 2 cycle. In particular, we will focus a bit more on M5 branes wrapping 3 cycle, because they, as could have been read from the previous equation, are able to form one of these higher link, and so they are able to have a more interesting dynamics. They do not just link with M2, they link with themselves. And I will give an interpretation of this phenomenon in a few slides. Before that, let me say that even in 5D, one is able to define a so-called one-form symmetry divisor. So you just have to, in this context, the compact 4 cycles intersect the curve inside the geometry, and this is how you define the charge of a M2 brane with respect to the divisor. Playing the game as I played before, I can just take a linear combination of divisors such that the charge of each curve with respect to this divisor is a multiple of n, and this is not a trivial divisor, and this gives me a way to construct a compact divisor that is associated to the boundary 3 cycle that encodes the one-form symmetry of the theory. And I pick here the case of SU1 Young-Mills because indeed they reproduce a divisor which is formally identical to the one of the 7D case. In this theory, one has as well to consider isometries. In the toric case, the one we analyzed is easy because the toric geometry have an SL2Z invariance. If I take the toric diagram of my Calabi-Yau threefold, I can transform it through some SL2Z transformation without changing the physics. In general, these are dualities, strong weak coupling dualities, not real symmetries, but it turns out that there are subgroups of SL2Z, in particular Z2, Z3, Z4, Z6, that can become good candidate as symmetries when my toric geometry is invariant under such transformation. This trick has already been used to construct gaugings, discrete gauging, 5D theories, etc. We are not interested in doing that. We are just interested in noticing that if, for example, in the toric diagram I do a 180-degree rotation, the toric diagram is formally identical. The only difference is that I'm going from a resolution where the compact cycle S1 is on the bottom to another in which is on the top. And so this, as before, is a sign that this transformation that leaves the geometry invariant, leaves even the physics invariant, because now I'm literally transforming the singularity back to itself. And so I interpret that again as a sort of symmetry, as an actual symmetry of my quantum field theory, as an action on the higher form symmetry, precisely because it has this non-trivial action on divisors that can be translated to a non-trivial action on boundary cycles. So with this said, let's go back to the new interesting ingredients that we have in 5D that we didn't have in 7D, sorry. In 5D, what happened is that if I consider SUN level K, I have this Lagrangian that I wrote up here, and the Chern-Simons term can lead to anomaly for the sentence symmetry. What does this mean? It means that if I have a Chern-Simons theory, SUN level K chance plus K in, sorry, SUN level K in 5D plus a Chern-Simons term, it might happen that it is impossible to gauge the one-for symmetry. So it does not exist as PSUN level K for any K, only for specific K. Which case? Well, this is captured by this computation that is from this work from Gukov, Pei, and Sin, where they showed that there's a Toft anomaly for the one-for symmetry associated to the level K Chern-Simons term. If this anomaly is non-vanishing, you're not allowed to gauge your one-for symmetry. You would end up with this would-be PSUN theory, level something, that is anomalous. This is not a Toft, once you gauge the one-for symmetry, this is not a Toft anomaly anymore, it's a gauge anomaly, so your theory is completely broken. And this is an interesting fact that pops up in 5D, and this is an interesting fact that is indeed captured by the linking number of branes. What happens is that if as I said before, if you just allow for all possible linkings of brane, and so not just the naive, quote unquote, action of M2 and 5, but you also consider the self-linking of M5 branes, what happens is that for k equal to 0, this equation can be solved by n5 equal to 3. So 3 generators of the one-for symmetry can form a non-trivial configuration. This non-trivial configuration will be labeled by a number, a topological invariant number that measures this configuration, sort of like a Milnor invariant for this Borromean style of linking of branes. This quantity can be computed by means, by the way, this is based on the original work on the SymTFT by the Oxford-Durham collaboration. And they were able to extract these coefficients by computing tripole intersection number. Tripole intersection number of the geometry can be pushed to the boundary and be like this higher and become this higher linking of branes. And indeed, this quantity becomes a purely topological quantity. This tripole intersection, local tripole intersection becomes a purely topological quantity in the boundary, this higher link. And this provides a way to compute the anomaly coefficients for the one-for symmetry of the theory. This is something, by the way, let me just, for the mathematician, there's a notion called Massey product. I don't know that much how it works, but this kind of analysis seems to point out that a simple analysis of the boundary geometry using just cap products and deltas might be not enough. Some richer structures, richer product as this Massey product might be the correct ingredient to add to your boundary geometry in order to capture anomalies as well. I haven't explored this into detail. In our work, we just pointed out that linking, this higher linking exists, can be computed and reproduce the known result. We don't know exactly what is the correct algebraic structure to endow your cohomology with in order to get them. But anyway, yes, this is the novelty about 5D theory and anomalies, and you get them just by, again, bottom-up requirement of everything can link, everything that can link will link, and this gives you exactly the expected dimensionality for the operator that participates to the anomaly. Finally, as a last example, and it will be the example that clarifies a bit more the role of isometry in the construction of the SymTFT and better understanding why we should consider them to have to capture fully the spectrum of topological operator of our theory, is the case of a 5D or 4D super Young means engineered again in M theory by means of G2 manifold. The G2 manifold we are using are constructed as a fibration over S3 of the ADE singularity. We really like ADE singularity. I think that by now is clear that is a very nice space, geometrical space. This fibration this is a singular geometry. The boundary has a homology that can be easily computed. So again, we have a list of all the topological operator corresponding to the one-for symmetries of our theory. We now also know that there are some special transformation, this biolomorphism that acts on the ADE singularity, and this can be translated on actions on the quantum field theory. And since these are outer automorphism of the Lie algebra, we also know how they act on the center. I mean, we can repeat what I just said before, but here let's come to the interesting part. So if I tell you, consider if I take G, this G here to be the Dn algebra, I will engineer for, I actually don't remember which n you need to pick, but let's say that I'm engineering spin for n as a gauge algebra. This is the Lagrangian style analysis, not the global aspect. By what is known in the literature, one would consider, oh, well, I have the boundary cycles, and the boundary cycles are Z2 times Z2. So if I had to write down the SymTFT, this topological theory that encodes all the possible global variants of my theory, I would write down a term for one of the two Z2s, a term for the other Z2, and that's it. I would miss the last two terms of this Lagrangian. If I consider isometry instead, not only I have to add a term capturing this A tilde 3 dA1 is a term that captures the isometry action, this Z2 outer automorphism of the algebra. But I also need to add this term, which is the cubic term, that captures the action of the one-form symmetry on the of the zero-form symmetry, this isometry on the cycles, the one that swaps the cycle. And so this extra interaction is something that you would miss if you don't account for isometry when you do this analysis of SymTFT and topological operator. I wanted to use this specific theory, this spin for n, because the SymTFT is known and has been analyzed already in many papers. And this idea of enhancing the SymTFT for your theory with some twist, with some further action, has been already explored in this paper by Kaidi and Mori Zhang, where they pointed out that the correct formulation for the SymTFT is not just in terms of cocycle, representing these Zn gauge groups, these Zn symmetries, but it should be, one should implement this, one should consider twisted cocycle, not just cocycles. And this twist is precisely what we trace back to the outer automorphism, the action of the outer automorphism on the cycles in the boundary. And so we don't have a formal, solid construction of, we only have noticed this fact, and we are putting together this two observations that from the field theory point of view, people have observed that when there are some action of, say, zero-form symmetry and one-form symmetry, one needs to, in order to write down the SymTFT, they need to consider this twisted cocycle. And what we are noticing here is that considering isometry is exactly what tells you that you should look further from the trivial analysis on the boundary and you should add something more. How to express formally that the correct object that encodes the whole data of the band of your symmetries and defects in the quantum field theory is exactly the twisted cohomology of the boundary. We don't have a refined statement for that, but we are pointing toward that direction. Like this is now more math work than physics, like to find the correct series of words that describe exactly how this isometry plays a role in the boundary geometry. But anyway, as I said, I just want to point out that this has been left over a bit in the literature so far and needs to be implemented in order to get the full spectrum of topological symmetries. Going now to the conclusion, let me review very quickly what I said today. So the boundary geometry has a lot of information. The boundary geometry gives you a list of topological operators that can be associated to brane, wraps in them, etc. But it needs to be supplemented with other data. It needs to be supplemented with the action of isometry that can be interpreted as symmetry of the quantum field theory, and needs to be supplemented with higher linking numbers that can lead to terms corresponding to anomalies that are not simply given by the crude boundary geometry homology. You need other algebraic structure in order to get all of this. A question is now, what is missing? Well, I don't know. What I can tell you that is missing definitely is continuous symmetries. As I said at the beginning, we know basically nothing about the continuous symmetry, or at least we know, we knew everything we could know about continuous symmetry until people started caring about discrete symmetry, and then we realized that we don't know much about continuous symmetry anymore, mostly because this symmetry TFT picture is not suitable to describe them. But it would be interesting to understand whether or not there's a nice bulk boundary sort of relation for continuous symmetry in the same way. For example, we know that in 5D CFTs, non-isolated singularity, the non-isolated locus describe flavor symmetries, and those are SUN symmetries, SON symmetries, like continuous symmetry. How do they enter in the game of the symmetry TFT? Do they have a linking structure? Do they bring new correction to the boundary homology in a certain way? If so, how? Well, this is, I mean, I have to leave something to do for the future. So this
Very kind of you.
Thank you very much for the attention.
All right, let's thank Shani. Do we have questions?
Hello. Yes, I do have a couple of questions.
Go on.
So yeah, first I wanted to ask about what you said about the ciphered manifolds for the refined version of the linking. Like, if you could say something about that.
Okay, I can go very quickly to some slide, just pointing out to some stuff that goes on. Since I have prepared them, let me use them. So, okay, this is not this one, this one. So this thing, there's a whole going back to homology, cohomology, etc. So let me explain to you how do I understand this story. If you take a BF theory, which is a theory of U1 connections, you require gauge invariance of the action, and this is invariant under the usual linear gauge transformation. You define some operators that are gauge invariant, and now you want to compute the expectation values of the insertion of this operator in the path integral. And this is achieved by adding to the Lagrangian some delta functions. These delta functions are nothing but the locus in which your operator are inserted. You compute the equation, you impose the equation of motion, and in imposing the equation of motion, when you arrive at this point, you need to do this D inverse operation. This operation is I'm inserting some loops in my spacetime, and now I'm declaring that to this loop gamma, I'm attaching a disk. So this delta function here, this delta of big gamma, is the delta function that localize on the disk, on the loop, and the disk attached to it. So the disk is the cipher surface, and this delta gamma is the Poincaré dual. So is what was appearing in the previous equation. If I do this procedure, it happened that the expectation value of this object is given by the op link of these two, and the op link is computed exactly through the integral of the wedge of these two delta function. One is the delta function that localizes on one loop, and the other is the delta function that localizes on the other loop with a surface attached to it. And the linking number is exactly the intersection between the loop with a disk on it and the other loop. So the way in which mathematicians say that two things link is if I take the two guys and I fill one of them with a disk, the intersection will counter. Now, this is step one. Step two is how do you do the higher linking thing? Well, that's a bit more complicated. For the higher linking thing, you can consider, for example, this action. You make it gauge invariant through some procedure which is analogous to the Green-Schwarz mechanism. You improve the gauge transformation. When you do this, and you impose, there are some further things, when you do this gauge invariance, when you do this D-inverse operator, you follow all the steps required by, there are some consistency steps that you can find in this paper by Putrov, Wang, and Yao. When you finish checking out that everything works the correct way, they explain it very cleanly. And this correct way just means that everything is gauge invariant from the beginning till the end. You end up with a weird expression that is not easy to write down, but that expression is precisely the nil non-invariant you get. And what are these not so easy to see constraints? The gauge invariance basically is forcing you to have the 3 loops, and gauge invariance requires that none of the 3 loops, the 3 circles intersect each other, but the whole configuration stays together. It's harder to say in words. It's easier to see it through the paper. They are really clean in this. But the punchline is, if you do just gauge theory with some BF-like action, and you require gauge invariance all the way through, naturally, constraints that tells you how you should put your loops in the correct way will arise as a consequence of this gauge invariance. And this will give you the structure of this higher linking number. So in a sense, the expression I wrote before of the higher linking is nothing but a sort of weird way to disguise a BF theory with a certain number of terms, interaction terms, cubic term, 4th power term, or etc. It is not super easy, but is a BF theory in disguise.
Okay, thank you. And I also had another question, which I guess is related to this last part of the story of the interaction in terms of the BF theory.
Mm-hmm.
So when you mention the construction of Kaidiomori chain of the SymTFT with twisted cocycles, I remember that had a problem with gauge invariance, because I think that, so
Okay.
there is a way to connect.
This is precisely
sort of.
Okay.
Yeah.
This is precisely why I took the spin for n example and not the SUN example. I have no idea how to write down the SUN example.
Yeah, because in SUN you have the, instead of the B2C2, you have the B2B hat, right?
Exactly. So spin for n, luckily, is the easy example in which the thing can be written explicitly, and is the only one in which I know that can be written explicitly. The other one is more like black magic to me. From their paper, I never really 100% understood how it works. I can understand how it works in this case, in which it's fine.
So, and then these tricks with the paper that you were citing now for improving gauge invariance in the BF theory with interactions, it doesn't work for the SUN.
No, okay. If you want, the tricky part of Kaidiomori-Zhang is that you cannot make the action gauge invariant, and so if I cannot make it gauge invariant, I don't know how to make the computation.
Yeah.
So this is if you want, this is an issue, is an open problem to my knowledge, that they write down something, they have a way to do some computation, but if you try to transpose, I guess that in this discrete realm it works fine. If you try to do the same thing with
I really don't think it does, because I think if you go through the twisted cocycle language, you also fail at gauge invariance because now the co-boundary operator doesn't square to 0.
Okay. Yeah.
I think
I remember that they have some comment like, "Oh, we limit ourselves to some gauge transformation."
Yes, but actually, if you then do your, because I know because we checked this, but if you do your example of they do the duality, which is a C4. If you do the example of charge conjugation, then it turns out that this restriction of the gauge transformation means that gauge transformation is equals to 0.
I see.
And then
I never entered too much to the details. I just got to the magic word, the twisted cocycle, and I know that this is the correct thing to add here. But I agree with you. Is not 100% clear how one would actually do computation with that at the end.
Okay, thanks.
Shani, can I ask questions on those ADE singularity you mentioned before? Like around maybe page 15.
Yes.
So you talked about those automorphisms here. So so for these three, the four automorphisms should be S3s, right?
Sorry?
So for if you just took these three,
Yes.
and the automorphism should be a S3, right?
Yes. Yes.
And
You can actually
realize it by like wrapping the branes on some cycles.
I don't think so. I mean, I know that there are some ways to realize some of these transformation, not in this context. I mean, there are holographic way to do charge conjugation, which requires D7 branes, for example, but I don't know how they translate to geometric engineering. Because here, for example, I don't have D7 branes. I just have either. So one thing that we were thinking, but it's purely conjectural, is something on the line of, okay, I can maybe take the O plane, they will lift to pure geometry and they become this whatever. I mean, I can say some words that means nothing to try to motivate how. But if you just play the game of M2s and M5s,
Yeah.
I don't see exactly how they could become this outer automorphism actually.
I see. I think for these three, there's a triality. So if you can realize S2 out of it, so you should be able to realize the other. No?
Maybe. We actually didn't, I don't remember. For sure, we have the outer automorphism. I don't know the triality, however, maybe I don't remember if we checked that. To be honest. We were happy with this result because they are quote unquote charge conjugation. I don't know actually the Z3 extra that you have for.
We saw it from.
You can see it from the.
The specific case of D4 as a special equation that when you can see that there is it's just yes for yeah.
Okay, so
One
yes,
is on isometry, yes.
Yes.
we have the debt. Sorry. Yeah, no, Mario did a whole analysis. You can take this equation, take the most generic matrix in GL3C to transform them, rotate them, etc. And it turns out that the most general transformation is always one of these transformation times something else, and the something else we associate it to should be associated to some conformal scaling transformation, something that anyway doesn't act on the compact cycle, the what that you blow up. Only these specific ones are the ones that actually change the moduli, so change the resolution, and so are the one of interest for our analysis.
Thank you.
Okay.
Do we have more questions? If not, then I would say let's thank Shani again. And we can go off the record.